Hello everybody, my name is Amirreza Zarnaghsh and today I'm presenting our work which is titled Quantifying Runoff and Baseflow Controls on Stream Turbidity. We know high concentrations of sediments in streams can cause many environmental issues including water quality degradation and aquatic habitat removal. We also know that the majority of sediments are transported to streams during storm events, when suspended sediment concentrations can increase significantly over short time periods. One of the challenges in controlling sediment pollution during storm events is that we are not sure which water component has a more important role in increasing suspended sediment concentrations. Is it surface runoff or is it base flow? We also don't know how urbanization affects these contributions. So in this study, we have used high-frequency 15-minute specific conductance and turbidity data to develop a new method that quantitatively explores the role of surface runoff and base flow in turbidity generation. So for our study area, we have selected 3 different watersheds in Johnson County. Blue River is a rural watershed with 21% of urbanization. Mill Creek is a mixed watershed with 62% of urbanization. And finally, we have Indian Creek, which is 90% urban. In the first step, we obtained USGS high-frequency 15-minute discharge, specific conductance, and turbidity data from 2002 to 2014. And then we developed an automated algorithm to identify 222 storm events during this time period. In the third step, we used our discharge and specific conductance data to split our hydrograph into 2 components, the runoff component and the base flow component. And finally, we use a multiple linear regression method to understand if turbidity variations is more aligned with dynamics of runoff and base flow water components. So in our multiple linear regression method, we are using turbidity as our dependent variable and base flow and runoff as our independent variables. And we are assuming that the coefficient of each independent variable is representing the importance of that variable in turbidity generation in our streams. So finally, we normalize these coefficients to come up with a single variable which is called beta prime runoff, and this variable varies between 0 and 1. So as it gets closer to 1, it means that the surface runoff is more important in turbidity generation in streams. So the results of our study are shown in this plot. Here the x-axis represents the peak flow during the storm event, and on the y-axis we have beta prime runoff. It can be observed that in the rural stream, beta prime is large for the storms with low intensity, indicating turbidity generation is more aligned with surface runoff for these types of events. However, as events intensify, we can see that base flow becomes more important in turbidity generation. Unlike the rural watershed, we cannot really find a clear relationship between beta prime runoff and peak flow in the urban watershed. Beta prime runoff is highly variable, and base flow can be a significant driver even during events with very low intensity. In this section, we have shown some sample storm events for each watershed, which are labeled by numbers in the previous plots. We can see that during some storm events, we have 2 turbidity peaks. One turbidity peak corresponds to the peak of runoff, and the other one corresponds to the base flow peak. But we also have many storm events in which one of the water components is actually contributing to turbidity generation, and we can't see any contribution from the other water component. This is indicating that beta prime runoff might be explained by variables other than land use and storm intensity. In conclusion, we can say human disturbances such as stream channelization and industrial discharges increase the capacity of base flow to erode stream bed and bank sediments. This, coupled with lower upland sediment availability due to removal of soil in urban areas, will cause base flow to have a larger contribution to turbidity generation during storm events.